Hello, in this video we're going to be referring to an older video, or the previous video, where we had three tanks that were in a series and we derived some differential equations to simulate the heights of the fluid in each tank. This was our final plot that we ended up with. So a quick review of how we got here was we started by deriving the equations. And so again, this was our problem where we had three tanks. This is our little diagram. We had a flow going in, and then we had flow defined as Q. So 1, 2 is from tank 1 to tank 2, 2, 3 is from tank 2 to tank 3. And basically, we took these and we wrote out an energy balance to derive this equation here, which represents the flow from each tank, and we use these to have the three for each respective tank. We also use an energy balance to derive the initial heights, which are the same at steady state for all the tanks. And then we used mass balance to derive these three differential equations here, which we then used in the Google Colab to code out the simulation. So going over here, just kind of a run through of what the code is. We first imported all of the packs in this first chunk here. NumPy was to have the mathematical functions such as linearly spaced plots and such. Plotly.subplots, we imported make subplots. This allows us to plot this figure here. And then scipy.integrate, we imported solve IVP. So this is so that we can solve simultaneous differential equations, which is what we have, once we provide an initial value. And we were given the initial value of the system at steady state. And so now, after we did that, we inputted all the givens. So G is the gravitational constant. On here on Earth, it's 9.81 meters squared per second. We inputted the initial steady state flow, which is 0.1 meters cubed per second. We inputted the area of the hole of the drain, which is 0.01 meters squared. The T end is the time that we ran the simulation for, that's 5,000 seconds, and the cross-sectional area of each tank is 1 meter squared. This is an equation that we derived from the energy balance to get the initial height. So it is the initial flow in squared divided by the cross-sectional area of the hole squared times 2 times the gravitational constant. And then after we did that, we defined the function for the right-hand side of all the differential equations. And so we gave it the independent variable, which is the time, and what the vector is v. That's the array that comes out. And we unpacked the array into the height of tank 1, height of tank 2, and height of tank 3 here. And then we use the equations that we derived to get the flow in and the flow from tank 1 to tank 2, flow from tank 2 to tank 3, and then flow out of 3. And the function returned in an array the right-hand side of each equation for each respective tank. And then we use the solve IVP method here to solve the simultaneous differential equations, and we gave it the name of res. So then when we created a plot, we created from 0 to the time that we wanted to run for, with 100 linearly spaced values, and we ran it for the time. Like I said, we wanted just a solution that's whole, and we have for tank 1, tank 2, and tank 3 heights, and then we made the plot, which is here. And that was a very quick and brief run through of what we did in the previous video. Obviously, you can go and watch the previous video. But now what we want to do is, instead of knowing that we increased the flow by 20%, we now want to have a specified set point for the height of tank 3. We want to control how much fluid is in that tank, or how much fluid height is in that tank. And so if we take a look back here at our diagrams, we're going to, instead of having a value that we increased the flow in by, we're going to change the flow in to have the height where we want it. And so what we can do is the most simple controller that we can put on it. We can put a controller on it to do this instead of sitting there and messing with the nozzle for the flow itself. So the most simple controller we can add is called a proportional only controller. This controller is very simple, but it does have a lot of cons. It is not very accurate, but you will see that in the simulation in a moment. And so to do this, basically, we have tank 3 here. And then we have all this stuff before tank 3, but we have tank 3 here with a fluid height in there. And let's say we want the fluid height to be here at this red line. If the fluid is below it, we want to up the flow in. If the fluid is above it, we want to lower the flow in. Pretty simple. So we have the set point. This is the red line for the height. That's what this is. Let's just say we want this to be 10% increased from initial height. Okay, so like I said earlier, it's going to be the set point minus the actual height, and that changes the flow. Well, what are we going to multiply that by? We're going to multiply that by Kc. And this is the nomenclature for a proportional gain. So this is just some constant to let the system know how much the flow needs to increase by based on the difference between the height in the third tank and the height of the actual fluid. And another important thing is, actually, let's just code this first. So we now have Kc, which we can just say Kc can be, we'll just start with some smaller number just so that it doesn't mess with the system too much. We'll do 0.005. And we need to change this Qn because now it's not dependent on the increase, but it's dependent on the set point. So actually we do need to also say the set point. That's going to be a 10% increase of the initial height. And then we're going to multiply this by Kc. Oh, hold on. Give me 1 minute. And if we take a look at the plot here, it doesn't look too great. So what is happening? Well, what is happening is this flow in is not changing with respect to the initial flow. So there's already some flow in it, and we want to change that initial flow. And so how we change that initial flow is we have to add, so going back to our equation here, we have to add in the initial flow rate. Because if not, it's just going to be like a new flow every time. It's not going to have any sort of meaning to the system unless we have some sort of meaning with the initial flow. So if we look here at the graph, it looks a little better. We're not reaching the set point, so the set point that we are trying to get is 5.6. So right now we're sitting at 5.3 maybe. Not exactly where we want it to be. So let's make the controller a little more aggressive. And how we can do that is by increasing this KC value, this proportional gain. So let's just increase it to 0.01. See what we get here. Okay, 5.3, a little closer to the set point. We're looking to get to 5.6, so let's try 0.03. And now it's oscillating quite a bit, but we are still reaching a steady point or a steady state eventually, but it's at 5.4. So let's try 0.05. Okay, it's still reaching a steady state eventually. There's still some kind of wiggles there. What we can do is we can, it's at 5.5, which is fairly close, but let's not quite the number we need. So let's increase the time, see if it reaches a little steady state a little better, and then we'll increase the controller gain to 0.07. Okay, so it's completely messed up. Let's kind of go back and kind of retrace what happened here. So let's decrease this again to, let's just say 0.02, and we'll decrease the time because that took a little long to run. And let's give it some more plots so that it looks like a little rough right now, so we can give it some more values. Okay, that looks a little smoother, looks a little better. And we still are only achieving 5.4, like we're not getting to the set point that we want. So 0.07 kind of broke it. Let's try 0.06. Okay, still breaking it, so we'll just sit at 0.05. It's kind of reaching steady state, not, there's still some wiggles here, so maybe we'll increase the time to 7,000. See if that makes it a little better. Okay, so there is that steady state there, but it is only getting to 5.5. And again, just a reminder of what steady or what height we want. We want 5.6. So it's close, but it's not quite there. But if we do any more of an aggressive controller gain, it has all these oscillations. And if we go to it, I mean, we have all these oscillations, but it's still like eventually going to reach steady state because you can see it's starting to converge. But the difference is if we go to 0.08, what happens is it's the opposite. So what happens is it oscillates so much, and eventually these values go to basically infinity. So if I increase the controller gain even more, let's see if it will, yeah, so here it says that it's an excess, that it can't calculate it because it's going to infinity. And so if we still sit at this we'll sit at 0.06, and we can just kind of extend the graph a bit and see how far it takes to reach steady state. So here it is, 5.53, which is 0.5 away from the actual equation that we want. So like I said earlier, the proportional gain is very simple. It's a very simple concept. It's very logical. You know, if it's too much liquid, decrease the amount that goes in. If it's not enough liquid, increase the amount that goes in. But it's not going to work the best because it's a system of three, and you're increasing the initial flow, and it doesn't account for many, many other things. This is just the most simple controller. But the biggest con is it doesn't get you to the point that you want it at. And so, yeah, it's not the best controller for this system, but it gets you fairly close. This is a simulation for that controller, and as you can see, it's not the best. These oscillations, even though it does eventually reach steady state, it takes a while, and these oscillations are pretty significant. So like let's say you have a limited tank space and you need it, like the set point is 5.6 and the tank only holds 6. You don't want it to go much greater than that, and so this would overflow the tank. And so there's just so many factors here that make the proportional controller not great for this situation, but this is the simulation for the proportional controller.